reason why I do it. Why do I draw the heart in this ridiculous way?
To get an understanding of where the blood comes from and where it goes out.
Exactly it. I doubt that you will ever see anyone else draw the heart like this, because the heart really doesn't look like this. What you just said is spot on, okay? Is that I want you to have a conceptual understanding of how the heart works, okay? Where the blood comes from, where the blood goes to, and why. Where the blood comes from and where the blood goes to and why. That the entire right-hand side of the heart is oxygen poor, okay? So everything that's here, that's close, you have your ribs and there's cartilage in the middle called your sternum, okay? So your heart is about the size of your fist and sits just left of your sternum. It sits right here. Okay, so the right-hand side of your heart here is all oxygen poor. This is the blood that comes back from your body. It has a reduced level of oxygen. So of course then the right-hand side of the heart pumps that blood to your lungs. Okay, in the lungs, the blood is oxygenated. So now oxygen-rich blood comes into the left-hand side of the heart. So the left-hand side of the heart is all oxygen-rich. Okay, you would then send oxygen-rich blood out to the body. So then the bottom left chamber of the heart is this really thick-walled ventricle. It's a very hard contraction because the blood that is here in the bottom right portion of my heart has to be pushed with such force that it can reach all the way down to my toes and all the way to the top of my head, okay, into the end of my fingertips. So the bottom the bottom left part of your heart is very thick and very, very strong. However, when IB asks you to draw the heart, please don't draw it like this, okay? And they actually don't ask you to draw it very often because the drawing is complicated. They almost always provide you with the diagram, okay? Speaking of diagrams, I'm going to post 3 different videos from YouTube. So here, they're saying it's about the size of your fist and it's in the middle of your chest, fine. And then one of the things that we have to be comfortable with the heart is that what we draw as a very static, stationary environment is this. It is moving all the time, okay? So this is not meant to show you this video once and have you just absorb all the content. Take this video and loop it, and there are, when you first watch it, turn the audio off, like I have here, and just watch the heart work. Look at the valve here and when it opens and closes, and look at the valve here when it opens and closes. Look at the semi-lunar valves here when they open and close, and start getting a feel for how the top half of the heart contracts and the bottom half. It's top, bottom, top, bottom, top, bottom. And then after you've watched this, I'd say probably 3 to 5 times, and watched it without the audio, then go back and unmute it, and then get all the vocabulary where they are talking about oxygen rich and oxygen poor, and this chamber and this artery and this valve, okay? But you have to see the heart as the highly dynamic and moving muscle that it is. You can't just see the heart as this stationary, thing. So I'll put this as a reminder for you to watch the video, and I'll post those pictures. So you have this image posted in the folder, yes? Yes. So if you have the ability to print, I would print it. If you don't have the ability to print or don't want to print, that's fine too. Then I would draw this to the best that you can. It might take you a while. Don't get too hung up with the connective tissue here. IB doesn't hold you accountable for that. It's more important that you understand chamber, valve, blood vessel. That's really what IB wants you to know. Blood vessel, chamber, valve, blood vessel. Okay, that's what they're after. So where do you want to start? I'll start wherever you want. Where do you want to start on this diagram? Pick a place. From to, let's go from. Where do you want the blood to come from?
From the lungs.
From the lungs. You got it. So that would be over here. So here you have blood coming in from the lungs. It's a cool place to start. All right, so if blood is coming from the lungs, What is the oxygen concentration?
Rich.
It's rich, okay? So you have oxygen-rich blood coming from the lungs. Since this is oxygen-rich blood from the lungs, which side of the heart is this?
The left side.
The left side. The left side of the heart is oxygen-rich. This side over here is oxygen-rich. Awesome. This blood is coming back from the lungs, which means that it's going to the heart. Since the blood is going to the heart, what type of blood vessels are these that carry blood to the heart?
Artery.
Those are veins. Veins carry blood to the heart. Okay. Arteries carry blood away from the heart. So if you think artery away, they both start with A. So these are both veins bringing blood back to the heart. Okay. This blood is being carried from the lungs. So what type of vein is this?
Pulmonary.
Pulmonary. Excellent. These are pulmonary veins. So the pulmonary veins bring oxygen-rich blood back from the lungs back to the heart. Okay? The pulmonary veins bring oxygen-rich blood back to the heart, and this oxygen-rich blood is dumped into which chamber? This is an upper chamber. So what do we call the upper chambers?
The left atrium.
They are the atria or singular atrium. And then which side of the heart is this?
Left.
Left.
So that's a weak L. Let's draw a stronger L. So that is the left atrium. I need to make that bigger. There we go. So there's the left atrium. Cool. Oxygen-rich blood in the left atrium. As the blood comes in, this valve is closed until this chamber is full. Once this chamber is full, this valve opens and the left atrium contracts. Actually, the two atria, as you'll see in the video, the two atria contract at the same time. So your heart contracts, boom, 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 top, bottom, top, bottom. Love dub is what we'll talk about next. It's always top, bottom. Cool. So then the name of this valve, what is this valve right here?
The AV valve.
Yes, the AV valve, atrioventricular valve, okay? Nobody says that, right? Nobody says, atrioventricular, but it's called that because it's the valve between the atrium and this lower chamber being the
Ventricle.
Left ventricle.
and it's the ventricle of the left side. Nice. So this valve then opens, but this valve closes. So as the atria contract, the blood then flows into the left ventricle until the ventricle is full. Once the ventricle is full, the AV valve closes. And now this valve that's tucked up in here opens. Which valve is tucked up in there? As this blood actually does a U-turn, what valve is that? You go, oh man, no, that's a good one.
Semi-lunar.
That's the semi-lunar valve. That's why I draw this way, okay? Because when that blood does a U-turn, it's tricky, okay? We're in the left ventricle. As the left ventricle contracts and the blood leaves through this semi-lunar valve. So that valve right there is this valve right there. That is a semi-lunar valve, okay? This is why we draw this like this first. Okay, so the blood does a U-turn. Those blood vessels actually point back up, and the oxygen-rich blood then flows through this semi-lunar valve to this big blood vessel here. This blood is going away from the heart. So what type of blood vessel is this?
Artery.
This is an artery. It is a huge artery called the aorta. This arch on the top of the heart is called the aortic arch, okay? So this is an artery. It is a specific artery called the aorta, and since it has this curved nature to it, like an arch, we refer to it as the aortic arch. Fine. Now, as the blood comes out the top of your heart, it's going to two different places. It's going to your upper chest, your arms, and your skull, okay? But notice this, the blood also goes down and then sneak it in here, down. And then for some reason down here, they don't draw you the aorta down here. This is called the descending aorta. Descending aorta. And where do you think this blood is going?
Somatic cells.
Yeah, it's going to the somatic cells of the lower body cavity. So it's going to your abdomen, it's going to your hips, it's going to your legs and your feet. Okay. So as the blood comes out of the heart, there's this huge blood vessel that comes out of the top of the heart called the aorta, and the aorta then splits. And you have your ascending aorta that then splits out at the back or at the sides of your neck and makes the carotid arteries here, or the aorta then dives down into your descending aorta that for some reason isn't on this diagram. So that's all oxygen-rich blood, and this goes to somatic cells. Of course, it's oxygen-rich. So that is all the left-hand side of the heart. That's awesome, okay? Now, one other thing I would like to add, this is only from your left lung. Do you see this over here? This is from the right lung. So this is also from the lungs. And these are also pulmonary veins. And then these two veins sneak along the back of the heart. And so there's actually two veins that lead into this atrium. This is from the right lung. This is from the left lung. Alrighty, so then the blood goes out to the somatic cells, and then the blood comes back, yes?
Yes.
Yes. Blood comes back here and here. Okay? Because here is the blood flowing down to your lower abdomen, your belly, your hips, your legs. Well, doesn't that blood have to come back?
Yep.
That's what this is. Okay? So this is from the somatic cells of your lower body. And do you happen to recall the specific name? Because this is a vein, of course, because it's bringing blood back to the heart. This is a vein back to the heart. And these two large veins then bring blood back to this chamber. But these veins have a very specific name. What's the name? Pardon?
Vena cava.
Yes. So these are called vena. Now, whether you say vena cava or vena cava is totally up to you. Medical people say them either way, okay? But do you see how there's a vena cava on top and a vena cava on the bottom? Okay, one brings blood back to the heart from your upper body. One brings blood from back to the heart from your lower body. So we refer to this as the inferior vena cava. What does inferior mean?
Hello.
Lower, less. It's usually not a compliment. Okay, well, if that's the inferior, then what do you think we call the vena cava on top?
Superior.
Superior, exactly. Again, don't memorize. Don't just memorize that this is the superior vena cava. Then there's no depth to your understanding. Okay, understand that there's two veins that come back to the heart, bringing blood from the lower abdomen and from the head and the chest, and they're the inferior and superior vena cava. Awesome. So then ultimately, this blood here is from somatic cells. So since this blood is from somatic cells, what is its oxygen content?
Oxygen poor.
Oxygen poor. Oxygen poor, but carbon dioxide rich. Cellular respiration, right? All right. So then this oxygen poor blood now dumps into the right-hand side of your heart. The right-hand side of your heart is oxygen poor. Now, it's all the same labels, except instead of left over here, it's right. So which atrium, that's funny. Which chamber is this? The right atrium, totally. So this valve closes while the right atrium fills. This valve then opens. Which valve is this?
AV.
The AV valve, right? Atrial ventricular valve. So once this chamber is full, the AV valve opens, the atria contract, both of them at the same time. So this contracts, so it's boom, 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 boom. That's why there's two thumps to your heartbeat, the top, the bottom, the top, the bottom. Your heart does not beat left, right, left, right. It's not the way it works. It's top, bottom, top, bottom, top, bottom, okay? All right, so then the blood leads into the lower chamber being the
Right ventricle.
right ventricle. The AV valve then closes. The right ventricle starts to contract, requiring the opening of the
Semi-linear valve.
semilunar valve. Okay, semilunar valve opens. The right ventricle contracts. The oxygen poor blood rushes through. Since this is oxygen poor blood, where is it headed?
The lungs.
To the lungs. Now here's what's cool. This goes to the left lung. Well, do you see how this blood vessel truncates? Do you see how it goes into a Y? This goes into the left lung, and so this over here goes to the
Right.
right lung. Right lung. I almost said the right lung. To the right lung. That's awesome. Like this. So since this blood vessel truncates, that's why then there's two sets of veins coming back. So this is an artery or a vein?
Artery.
It's an artery. What kind of artery?
Pulmonary.
Pulmonary artery. So this is where people start getting confused because almost all of the arteries in your blood, in your body, carry oxygen-rich blood. Almost all of them. So then you will hear people say, oh, the definition of an artery is that it's a blood vessel that contains oxygen-rich blood. That is not accurate. What artery in your body carries oxygen-poor blood?
Pulmonary.
The pulmonary.
Pulmonary artery. Okay, so don't ever let anyone define arteries oxygen-rich, oxygen-poor. That's not how you define arteries. Arteries and veins are defined by the direction of blood flow according to the heart. Okay, if the blood is flowing away from the heart, it's an artery, thus away artery, away artery. Veins bring blood back to the heart, thus here back to the heart, vein, back to the heart here, vein. Hey, there's the heart. Okay, now sometimes when students see this, this is overwhelming. Okay, don't let this overwhelm you. So don't start here, start here. And understand vena cava, atrium, valve, ventricle, semilunar valve. Then pulmonary vein, then atrium, valve, ventricle, valve. Understand that process, and then left and right, oxygen rich, oxygen poor, and then that will make this make a lot more sense. Now, when you study this, don't study this diagram completed. How should you study this diagram?
Without notes.
Yes, study it blank. Okay. The mistake that students make, especially with human anatomy and physiology, is you study the diagram and it's completed when all the answers are there. And you go, oh, I know that, right? But then you get the test for IB and the diagram's blank. And the way that you studied and the way that you test don't match, okay? So somewhere on here, write yourself a reminder to study this blank. So usually, if we were in the classroom, I would give you 2 copies of this, one to write all over and then one to study. But since I posted it electronically, you already have it. So study blank. And this is true of any human anatomy and physiology diagram. Study the blank diagram so it matches the format of the test. And then looking back at this, I should put a label there. What should I put there? Where's that blood going?
Into the body.
Yes.
Somatic cells.
Yep, to the somatic cells. I don't know how I missed that, but I did. Okay, so go through this, repeat it to a friend. I don't know, you're riding on the bus, pull it out and say, let's talk about your heart. No, the way that you learn this is simply by talking about it. And just get that vocabulary to come out of your mouth, and it will make your life a lot easier. Cool? May I take this?
Yep.
Cool. All right. So we need to talk about heart contraction. We need to finish up question 2A. We'll get a little bit into 2B, do a diagram, and call it a day. So 2A wants you to address the heart contraction. So you want to draw a heart like this, which now begets the question, why? Why do people draw the heart like this when the heart doesn't look like that at all? I don't know. So this is going to be step 1 to step 2, step 3, such, and then it's going to be 1, to 2, 3. And then we'll come down here. Why does that feel so far away to me today? Interesting. And here's what's going on in the left-hand side of the heart. Boy, I almost wrote that on the wrong side. That was close. Almost did. All right, T-chart. Then we'll talk about what happens in step 1, what happens in step 2, and what happens in step 3, because what's happening on each side of the heart happens simultaneously. That's why it's so important for you to watch that video. All right, so let's go on the right-hand side of the heart. So we're dealing with this side of the heart here. Oxygen rich, oxygen poor on the right-hand side.
Poor.
Poor, I agree. Oxygen poor blood returns to the heart through the vena cava. That would be both superior and inferior. Boom. Blood's coming back to the heart through veins. Whereas on the left-hand side of the heart, same thing's going on, but how is this statement over here different from this statement? Oxygen rich. Yep.
Mr. Banner, what does
Yeah.
SI stand for?
Superior and inferior. I want you to be aware that there's 2 vena cava coming back to the blood, coming back to the heart, excuse me.
Okay, thank you.
Thank you for asking. Returns to the heart through the pulmonary veins. I want to add that. This is going to be superior and inferior. Boom. And this is oxygen rich. Love it. So then step 2. The blood enters which part of the heart?
The atrium.
Yes, the right atrium. Whereas over here, the blood enters the left atrium. Again, driving the point home that the right-hand side of the heart is oxygen poor, while the left-hand side of the heart is oxygen rich. So I assume that you understand that while the blood's pouring in, the valve at the bottom is closed. The valve at the bottom of this chamber is called the
AV valve.
AV valve. The AV valve now opens, and the right atrium contracts. Over here, same thing. AV valve opens, and the left atrium contracts. This is all a coordinated muscle contraction. Okay? This is the first thump of your heartbeat, what people refer to as the lub. It's a softer contraction. If you really sit quietly, really concentrate on your heartbeat, you will feel how the first contraction is softer, the second contraction is harder. It's a lub duh, lub duh. That second contraction is harder. So this is the lub, or the first beat. I assume that you know that your heart goes doom, doom. There's 2 thumps. That's top, bottom, top, bottom, top, bottom. And this isn't just our heart. All mammalian hearts look that way. The cat heart is about the size of a golf ball. A whale heart is about the size of a basketball. Okay? Anatomically, though, identical. right? Our heart, a pig's heart, a cow's heart, a cat's heart, a whale's heart, identical because we are all mammals. Okay? That's why at some point you and I will return to the classroom. I don't care if it's semester 2 or I don't care if it's the summer of 2021, and we're going to put some cats on those benches, and we're going to open those babies up if you're interested, and you're going to handle a mammalian heart, looks just like yours, except instead of being the size of your fist, it's only about the size of a golf ball. Okay? You got to see it, got to touch it if you're interested. If you're not, then that's fine too. I understand that. All right, may I take this?
Yes.
Yes.
All right, so now let's do the bottom contraction, the dub, the harder contraction, okay? So this contraction isn't so much step 1, step 2, step 3. The top part of your heart squeezes, okay? It actually starts from the top of the heart and does this. It's actually a gentle squeeze, okay? The bottom half of the heart isn't so gentle, okay? The bottom half of the heart, the contraction happens all at the same time. It isn't this gentle squeeze. It's the whole bottom half of the heart all at once. Bang, like this. This squeezes, almost like a tube of toothpaste from the top to bottom, like it squeezes, and this is all at once. So same thing, let's put a line down the middle of this. So now you guys are going to sit in 4th period. Just feel it. Thank you. Thank you. Thank you. Because you will find out on Thursday that we don't know what makes your heart beat. There's a little piece of neural tissue in your heart that causes muscle, well, it does. It causes the heart to contract, but we don't know what actually stimulates that contraction, so we call it spontaneous. We still don't know what actually makes your heart beat. It's fascinating. All right, so we're going to put 4 bullets in here, so let's put the first one in. So the blood has now entered the lower chambers, okay? So there's a valve on top of this chamber, yes? We are now in the ventricle. So what valve is above us? If we're in the ventricle, what valve is up there?
The valve.
The AV valve. So now the right AV valve closes. And the left AV valve does the same thing. Well, if you close the valve on the top, what does the valve on the bottom have to do?
Open.
Open, okay? So the right semilunar valve opens. Same thing here. Except not right, and row. It's funny, the thought crossed my mind, don't write right. And since I thought right, it came out of my hand, of course. Semilunar valve opens. Boom. And now, since the valve on top is closed and the valve on the bottom opens, what do you think the chamber does? Yeah, it contracts. What kind of blood leaves the right-hand side of your heart?
Oxygen poor.
Oxygen poor. While on the other side, oxygen-rich blood leaves for the somatic cells. This is referred to as the dub, lub dub. Which is the second thump, the second beat, boom, boom. Much, much, much stronger. So then the question is, why? Why is this heartbeat stronger? May I take this?
No.
No? Okay. How about now?
You can't.
Okay. It's funny, I just pulled that handout out and I put it away. There we go. So look at the walls of the ventricles. You see how the wall of the left ventricle is much, much thicker than the wall of the right ventricle? Why? Why is this wall so much thicker than that wall? Why is red thicker than yellow?
The distance the blood has to go.
Exactly right. Be sure and write that down. That's spot on. The distance that this blood has to travel is much farther. This blood is going from the tip of your head to the end of your fingertips down to the tips of your toes. This blood has to be forced harder, okay? Whereas this blood over here only has to go about 20 centimeters to your lungs. Only has to go about this far, okay? So this part of the heart doesn't need to be nearly as thick. This part has to be thicker. Okay. Now, getting back to evolution, you will hear people say, oh, the right-hand side, the left-hand side of the heart is thicker because that blood needs to go farther, as if the heart knows, oh, I need to push farther. Not the way it works. Okay. You have two organisms sitting side by side. There's variation in the population. The walls of the heart have different thicknesses. Predator pops out. We now start running so that we're not eaten. The individual with the thicker walled heart pumps oxygenated blood more effectively and therefore can run longer distances faster and for a longer period of time, thus getting away from the predator. And what happens to the individual with the thinner walled heart?
You get eaten.
Yep, because they're not as effective at getting away from the predators, so they run out of gas earlier, the predator eats them, and the thin walled heart becomes less and less common in the population. Okay, I keep coming back to variation because that is at the heart and soul of evolution. Okay, this idea that a characteristic is that way for the pumping of the blood, that's backwards. Okay, there's variation, and the individuals that are fit survive and pass that on to their offspring. So evolutionary fitness, again, is so much more than just physical fitness. It could be the lining of your intestines, or it could even be the muscle thickness in your heart. Ever heard of a heart attack?
Yes.
Yes, a myocardial infarction, okay? So myo meaning muscle, cardio meaning heart. So myocardial is heart muscle. Infarction is the fancy Latin root for cell death. Okay, so a myocardial infarction, if you read it backwards, is death of the muscle cells in the heart. That's the technical term for a heart attack is a myocardial infarction. Sometimes people have a heart attack and they survive it. Sometimes they have 2 or 3 heart attacks and they survive it. Sometimes a person has a heart attack once and they drop dead. Okay, it's location, location, location. Okay, so it all depends on what part of your heart dies. Okay, if anywhere in the top of the heart dies, you're going to survive that. Why? Because when these cells die, they don't contract, or that part of the heart doesn't contract nearly as hard. But does the blood in the atria have to go very far?
No.
No, it needs to go about 3 to 5 centimeters. It needs to go about this far. So, in all honesty, are the atria a good place to have a heart attack? Yes.
Yeah.
Okay. Now, if you had to choose between the right ventricle or the left ventricle to have a heart attack, which is better with the ventricles?
Right.
By far. Okay. If you have a heart attack here, it's much more serious than up here. Okay. If these cells in this chamber die, this is more serious, but you can survive it. You're not going to be as healthy. Okay, these are individuals that have a heart attack and they don't fully bounce back. They don't have the same stamina. They might even be on an oxygen tank. They'll survive it, but they're not nearly as healthy after the heart attack. Individuals that have a severe heart attack over here, they don't survive. Okay, they don't survive because now you lose the ability to send oxygenated blood out to your somatic cells, and so that causes the death of the entire organism. All right, so you can have a couple, 3 heart attacks up here and survive them. You can have a heart attack down here and survive it. You won't be the same, but you survive. And the people that have the heart attack down here don't survive them. So it's location, location, location. Super important.
Mr. Manor, what happens when you have a stroke? Like what happens to your heart?
Okay, so a stroke is because there's strokes and embolisms and aneurysms. Those have more to do with the blood vessels and not the muscle itself. A heart attack has to do with the muscle tissue of the heart. Okay, strokes have to do with the blood vessels, when the blood vessels tear open and rupture. And then depending on the tissue that is supplied by that blood vessel, that's why the stroke then causes the death of those cells. So you can have a stroke, you can have a blood vessel rupture or hemorrhage in the heart, and your stroke is here. Or you can have, more commonly, the blood vessel pops here and you have a stroke up here. Okay, that's why when someone has a stroke, it affects their muscle coordination. They will have palsy. Their arm will go limp. There will be paralysis. They'll be paralyzed. The muscles of the face, rather than having tension, the muscles of the face will relax, and so you'll see the muscles sag. That's called palsy. Right? The person might have difficulty speaking. They'll have slurred speech because the muscles of the tongue they've lost control of. And so they'll start talking like this because they only control half of their tongue. So depending on what part of the brain dies in a stroke depends on what your symptoms are. It's super serious. Okay, that's why when you learn all this biology and you're healthy, you go, oh man, I'm healthy. God, let's get some work done today. Why? Because I'm healthy. There's so many things that can go wrong. And one of these things eventually is going to get all of us, right? Don't be afraid of it. That's the flip side of the coin of being alive, is that one day we won't. Okay, don't dread it. Just understand that I'm going to get some positive things done before this gets me. Okay, I'm hoping or in my sleep, just nice and quiet. Yes.
So if someone has a heart attack in the left ventricle, there's like no way to save them, even if you do CPR and you keep pumping up their heart?
Yeah.
Because wouldn't you still be like kind of still keeping it going in a way? Like there's no way.
Yeah. What you're talking about is one of the most serious decisions that healthcare workers and family members have to make. Okay. Because when you're doing CPR, it's not quite as good as the heart still beating. So usually they will only do CPR for about 7, 10, usually no more than about 15 minutes, because you're still not getting 100% of the oxygen into the blood. And so you start having oxygen deprivation in the brain. And after about 10 minutes of CPR, you start having brain damage. Okay. So there's a really, really heavy duty decision where you're doing CPR, you're looking at the time and you're thinking, wow, it's been 10, 12, 15 minutes. We might be able to get this person's heart restarted and we save their life, but they might have moderate to severe brain damage. So now you're talking about, we revived this person, but what's their quality of life? And I mean, you don't get much more serious and heavy than that. Okay. My mom had to make that decision with my dad because my dad had a heart issue at the house, and the paramedics came and they worked on him, and they had her make the decision. They asked her, when do you want us to stop? And she had to make that decision. That's been 14 years, and that emotion is still, every time I talk about that, man, is right there, because that's a heavy duty decision. Do you get any more serious than that? So the answer to your question is yes, you can keep the person functioning temporarily with CPR. But at some point, since you're not getting all the oxygen into the brain, it leads to brain damage, and at some point you stop.
Okay.
Yeah, I know. And I understand the question, and I apologize that the answer is so heavy. That's a heavy duty decision. Okay. Okay. Can we talk about grandma's feet before we stop for the day? Let's talk about grandma's feet.
Yes.
Let's do 2b. So you have some formal event, and grandma decides that she's going to wear high heels, right? And so she wears high heels. How do grandma's ankles and feet feel at the end of the day?
They hurt.
They hurt. And so,
Extremely painful.
yes. So what I'm trying to draw here is grandma's foot. So phallic. That's supposed to be a foot. Here, I'll label it foot. Okay, it's grandma's foot. All right. So here's how this works. You have grandma's heart up here, and grandma's heart is pumping away. And there's blood vessels that come down to her feet, like such. And these blood vessels start big, and they gradually get thinner and thinner and thinner. I'm trying to make these thinner, I swear. Thinner, 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 like this. So this is the blood vessel that brings blood away from the heart and to grandma's feet. So what kind of blood vessel is this, since it's going away from the heart and to her feet?
Artery.
It's an artery. Excellent. And this is what we'll talk about on Thursday about the different types of blood vessels, because now this artery gets smaller into what's called an arterial, and then the arterial gets really small into what we call a capillary. And there are these little, tiny hair-like blood vessels called capillaries. And you've actually seen capillaries, because when we don't sleep enough, have you ever seen how the white of your eyes gets those little red lines in them? Yes? Okay. Those are capillaries. Okay. Those are the smallest blood vessels they are. And so then there is a capillary bed here, and this is where gas exchange happens. And then it's time for the blood to leave. All right, let's go over here. Let's do this. So you get another, it's called a venule. Get out of here. Here we go.
Wait, Mr. Manuel, did you say
Yes.
gas exchange?
Gas exchange, GAS, as in oxygen comes out of grandma's blood and carbon dioxide goes in. Gas
Okay.
exchange.
I thought it was like farting.
Grandmas don't fart. They're grandmas. And this is, of course, a baby. And then the blood leaves grandma's feet. Like such. All right. So think about the heart. The heart is nothing more than a pump. When the heart contracts, blood is pushed. Boom, boom. But does the heart beat all the time? Is the blood constantly being pushed by the heart?
No.
No. There's a pause in between, right?
Yeah.
So if there's a pause in between, as this blood, grandma's heart contracts, the blood goes up her calf, but then there's that half-second pause in between the beats. What does gravity do with the blood in the veins? What does gravity do?
Bring it down.
Pulls it back down. So then her heart beats and blood pulls it, and gravity pulls it down. Heart beats and the blood will be pulled back down. So in your veins, there are valves like this that are pointed up, right? So let's draw that over here on the side. So here's the wall of your vein, and there are valves that do this. So as the heart contracts, the blood drives past the valve. So veins have valves. There's no connective tissue here. There's no muscle connection here at all. It's simply a flap of tissue. And when the heart contracts, blood pressure increases, the blood pushes by, and the valve opens, okay? But then when the heart pauses and the blood starts to be pulled, that blood column that starts to be pulled by gravity, when the blood hits the valve, it simply pushes it closed. And so it's heart contracts, heart relax, heart contracts, heart relax, heart contracts, heart relax, okay? But what do you think happens as we age when these valves rub on each other? Do you think they make a nice tight seal?
No.
As we age, the valves start to do this. Well, since the valves do this, what slips back between the valves?
Blood.
The blood. So as grandma spends a lot of time on her feet, especially in heels, because it lifts her feet, it arches her ankle and actually reduces the effectiveness of the valves, more and more of this blood starts to accumulate in her feet. And what happens to her feet?
They get swollen.
They get swollen. And when it becomes swollen with tissue, how does that feel?
It hurts.
It hurts. Okay. So how do you help grandma out? Easy. You sit grandma down. You take her legs and you get her legs taller than her heart. Because then what does gravity do with the fluid from her feet?
Pushes it up.
Yep, pulls it out. Then if you want to help grandma out, you go to the sole of her feet. If her toes are here and her heel is here, what do you do to the sole of her feet?
You press it down.
You press it down and you go from the toes to the heel. Don't go from the heel to the toes. You're driving the fluid into the foot. That's mean, okay? Go from the toes to the heel and push the fluid out of the foot, back into the heel. The heart will then contract and it'll drive the fluid back up the leg. This is also true of any of you. If you wear tight shoes for a long period of time and you take those shoes off and your feet ache, simple solution. Elevate your feet higher than your heart. Gravity will then start pulling the fluid out of your feet, and then get somebody and say, hey, I want you to rub on my feet. I want you to rub my feet from the toes towards my heel, and do it on both sides. And you're literally milking the fluid out of the foot back into the ankle, into the calf, and your feet will feel better in about 10 to 15 minutes. It's easy. And it'll make you really popular with the other people in the house because you know how to give a good foot massage. It's simple. It's biology. So I think that's a good place to stop. Yes?
Yes.
Please do me a favor and look at the alumni list and pick out a couple of people there, and then go back to our folder. And in the senior folder, there's a spreadsheet. And if you could type the individuals that you want to contact, and then I will get you their contact information. If you could give me that list by Friday so I can work on it over the weekend, and you will have their information.